please. You need to have that out in front of you so I can check that it's done. Through question 6 on the 2 pages. All right, let me come around and check your reading guides for chapter 6. Okay. Okay. Thank you. 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 Good. Thank you. Thank you. All right. So Mr. Z told me there was a little issue with the video Friday. No?
Yeah, we said like 3 minutes left.
So there was just like a minute or 2 left? Okay. Were you able to watch it at home? Finish it up? Good. Okay. Then there didn't have to worry about it. Let me just end Grace's pass so it doesn't show that you were a delinquent. An administrator comes to find you later. How come took you 50 minutes to get to room 152? I hate this program. Oh, and it's for Mr. C. Forget it. That's it. You're a delinquent anyway. My brother. Yeah. His passes don't work here. Sorry. I'll yell at him later when I see him.
I guess I'm taking
That's it. No. All right. Here are your answers to the true false. Check it out. Number 1 is false. 2 is false. 3 is true. 4 is false. 5 is true. 6 is false. 7 is true. 8 is false. 9 is false. 10 is false. 11 is false. 12 is true. All right, let's go over them. Why is 1 false? Nick?
Because it can be positive or negative work, but it doesn't show direction. It just shows like.
Yeah, work can be positive or negative, and kinetic energy is unsigned. Okay, kinetic energy is unsigned. Right? You're never going to put a sign on it. It's a scalar. Scalars don't have signs. But the positive or negative on work would tell you whether kinetic energy was added into the system, it increased, or it decreased. So work will have a sign to tell you whether it's a change in the kinetic energy as an increase or a decrease, but that's it. All right, number 2, why is this false? It says the work energy theorem is best applied to problems where the force on a particle is known explicitly as a function of time. Why is that false? Nick? Yeah, function of position, not time. If you do force as a function of time, this integral, force as a function of time gives you an impulse, just so you know. That would be impulse, not work. Okay, number 3 was true, so I'm skipping that. 4, when several forces act on an object, The total work done on all of them is always equal to the integral of the net force with respect to position from position 1 to position 2, where the net force, F net, is the net force acting on the object. Why is that false? Has to do with the fact that it's an object. Matt?
It can be like internally, like rotating,
So why can't you use F net?
because that wouldn't be a particle.
Yeah, it's got, this would only be true if it were a particle. If it were a particle. Okay, because when you have an object, not all parts of the object don't always have to have the same F net. They can be moving differently. All right, so the issue is that not all points on an object have identical displacements, and that's why we would have a problem. Okay, this is only true if it's a particle. So to change this, we should really just say particle here and a particle here. Okay, number 6 was true, or 5 was true. I'm skipping it. Let's go to 6. When a particle moves in the direction of a conservative force, the potential energy of the particle increases. Why is that false? In the video, I told you what the best example of a conservative force was. What's the best conservative force we can think about? Starts with a G, ends with a Y. Mark? Gravity. So if this particle is moving with gravity, is the potential energy of that particle increasing? What is it doing? It's decreasing. There you go. It's going to decrease, not increase. That's why that's a bad, incorrect statement. 7 is true. 8. The reference point for gravitational potential energy must be mean sea level. What is it, Jerry? Matt? Yeah, any point. It's arbitrary. You pick your point for where you want gravitational potential energy to be 0. It will be told to you in a question. 9. An athlete throws a ball. To throw the ball again so it moves with twice the speed requires the athlete do twice as much work. That is a false statement. Why? If you want twice the speed, you're not going to do twice as much work. What are you going to do? Nick? Nope. I want to know how much more work you need to do to give it twice the speed. Ruben? How much work are you going to do to give it twice the speed? It's not twice as much. 4 times as much. That's right. Because if the work is equal to the change in the kinetic energy, if you have twice the speed here, right? Speed is squared in the kinetic energy equation. That's a quadratic relationship. You're going to have to square a doubled factor, which gives you 4 times the amount. Number 10, a particle is in stable equilibrium at a point where its potential energy is a maximum. That's right out of the notes. That's incorrect. What type of equilibrium is it if you have maximum potential energy at that point? Unstable, that's right. Or stable equilibrium, what kind of point would it have to be? Minimum, that's right. Number 11, particles that attract via conservative forces have more potential energy when they're close together than when they're far apart. That's an incorrect statement. Think about like with gravity, Earth and my pencil. Where does it have more potential energy? When the pencil is close to the Earth or far away? When it's far away. So that's a false statement. It's actually less when they're far away. You have less potential energy when they're close together, or more when they're far apart. And 12 was true. Okay, any questions on the other true, false? The true ones that I skipped, maybe you thought they were false. I can explain why they're true. No? Okay, next page. You pick a book up off your desk and you put it on a bookshelf on the wall above the desk. What's the total work done by all the forces acting on the book? Grace?
I said 0 because there's only a change in potential and not kinetic.
That's correct. The total work done is the change in the kinetic energy. The kinetic energy is not changing. It starts with no kinetic energy. It ends with no kinetic energy. So the work done total is 0. Your hand did work. Gravity did work. They cancel each other out. So the total work is 0. Number 2. A pendulum consists of a 1-inch diameter steel ball with a mass of M, which is suspended from the ceiling by a string. As the ball swings from its lowest position, where it has a speed of v0, up to its highest position, where it reverses direction, what is the total work done on the ball by all the forces acting on it? So let's start with that. How much work is done from the lowest point to its highest point? Matt? No. Total work is always equal to a change in kinetic energy. Lowest point to highest point. Is the kinetic energy changing? How much is it changing by? Use the variables in the question. The variables are M and V0. Tell me how much work was done as it goes from its lowest point to its highest point. Figure out what the change in kinetic energy is. Nick? Nope. Maddie? Almost. You're closer. Negative. Because you have to take the final value and subtract the initial value. 0 is the final kinetic energy because it stops. 0 minus a half of mv0 squared is negative 1/2 mv0 squared. And yeah, you got to use m and v0. You can't just say v. What v? The v in the question was v0. You have to make it specific to the variables in the problem. So negative 1/2 mv0 squared. All right. Now, how much work is done by each force that's acting on it? Can you tell me what the forces are that are acting on this pendulum as it swings from the lowest point to the highest point? I'll give you a hint. There are 2 of them. Name the 2 forces acting on this pendulum as it swings from the lowest point to the highest point? Olivia? And gravity and tension. Let's start with the amount of work done by the tension force. That one's the easy one. How is the tension force directed compared to the velocity? Perpendicular. So how much work can the tension do? 0. All right. How much work is therefore done by the force of gravity? If the total work done is negative 1/2 mv0 squared. Maddie? Yeah, gravity's got to do all of the work then. All right, number 3. A block of mass M is released from rest, and it slides down a frictionless incline and reaches the bottom with a speed of Vf. What is the total work done on the block? How do you find total work? Jerry? Thank you. The change in kinetic energy. What is this block's change in kinetic energy and therefore the total work? Use the variables in the question. It tells you you have a mass of M, final speed Vf. Giovanna, can you tell me? No. Positive. Yeah. So it's just 1/2 mvf squared. The final kinetic energy is 1/2 mvf squared. The initial kinetic energy is 0. So the total work or the change in kinetic energy is 1/2 mvf squared. Now, how much work is done by each force acting on this block? I'm going to give you a hint. First, you got to tell me what the forces are. There are two of them acting on this block. Name the two forces acting on this block. Jackson, can you tell me?
Gravity.
And that's right. How much work, the other Jackson, is being done by the normal force? No. How is the normal force acting compared to the velocity? What does the word normal mean? It starts with a P, ends with an R. Ruben? Means perpendicular. The normal force is perpendicular. So how much work can the normal force do? 0. So how much work, Robbie, is gravity doing? That's right. Gravity's got to do all the work, which was 1/2 mvf squared. And what component of gravity is doing the work? Only the parallel component is doing it. The perpendicular isn't going to do it, but it doesn't matter. The parallel and perpendicular together make up the force of gravity. Number 4, when you get up from your chair and you start walking toward the door, your kinetic energy increases. What force is doing work on you to cause that increase in your kinetic energy? And where is that kinetic energy coming from? What is doing work on you to increase your kinetic energy, Matt? Static friction. And it's really coming from the chemical potential energy that's in your muscles. Now, this idea of total work equaling change in kinetic energy would only hold for a particle. You are not a particle. You are an object. So we would not find your total work by using the change in kinetic energy, but it's coming from the static friction force that causes you to accelerate there. And that is a change. The change in energy is coming from the chemical potential energy in your muscles. All right, number 5. A car of mass m is traveling up a long straight hill of height h at a constant speed, assuming air drag is negligible. How much work is done by each force acting on the car, and what is the total work done on it by external forces? Okay, first of all, can you name the forces acting on this car? See if you can name at least one force acting on the car. Jerry? Okay, I got that one. I'll write that one down. So we have gravity acting on the car. What else is acting on the car, Nick? Yep. What else is acting on the car? There's one more. Ruben? So somebody is outside the car pushing it? No. Normal. That's it. Okay. Let's start with the work done by the normal force. How much work is being done by the normal force? Maddie? Because to the velocity. Okay. How much work is going to be done by gravity? First of all, can we say that the work done is equal to the change in kinetic energy for a car? Is a car a particle? So we wouldn't say that. Okay. So work done by gravity would actually equal the negative change in potential energy. So that's what we would have to come up with here, that the work done by the force of gravity would be negative mgh. That's it. Okay, that's the only way you're going to be able to do that. Work done by a gravitational force is always equal to the negative of the change in potential energy. Work done by the force of friction you can't find because this would equal the change in kinetic energy here. That change in kinetic energy is 0. How do I know the kinetic energy is not changing? What's the key in this question that is going to tell us that there's no change in kinetic energy? Jerry? Constant speed. Okay, so there's no energy there. Okay. And lastly, number 6, this is not a possible situation because the change in height is always positive. It went from lowest to highest point, so that's not possible. You can't get a negative value for the change in potential energy. Not from lowest to highest point. You can from highest to lowest, but not lowest to highest. They had it backwards. Okay? All right. If you want to keep out your notebook, you can, but I'm now going to go over the show work section of your last test. You may not write on this test. You may not write on this. You can take notes in a notebook if you want, but not on this. This is coming back to me in just a minute. This section that you just took, the chapters that we finished on 4 and 5, are worth about 20% of the AP exam. That's 1/5 of your test in May. So it's really important that if you did not do well on this, that you start doing some remediation to figure it out, and soon, because you have a midterm exam in a couple weeks where this is going to be on it. Follow along with me with question 1, please. I'm going to go pretty quick. Follow along with question 1. Do not look ahead. Start with me on question 1 so you're paying attention to what should have been done. I'm not rereading it. You recall the problem. Part A wants you to draw free body diagrams for the 2 students. Let's start with student B. The forces acting on student B are a tension force pulling the student up and their weight pulling them down. The force is acting on student A. Student A is touching the ground and a rope, which means that the rope is going to pull student A up, and then the ground is also going to push up, normal force, and student A's weight is acting straight down. Now let's go to part B. Now I want you to find the magnitude of the force exerted by the floor on student A. That means what is Fn? Student A is not moving, which means the sum of the forces on student A must equal 0. That means the tension force and the normal force must balance the weight of student A. Now, I'm not allowed to leave my answers in terms of any variables. I gave you numbers in this question, which means you have to figure out what the tension is that's in the rope in order to find Fn. The way you're going to do that is by now looking at student B, which is also at rest and therefore has no net force. That means the tension must equal the weight of student B, which is found by doing the mass of student B times gravity. So that is what I'm going to plug in for this tension. MBG plus Fn. And how do I get the weight of student A? MA times G. So the normal force is the difference in the masses times G. When I bring that MBG to the other side, it gets subtracted. I'm just factoring out the G. So let me go ahead and plug in 70 kilograms for student A minus 60 kilograms for student B times 9.8 meter per second squared gives me a normal force. So that's 10 times 9.8, which would be 98 newtons for that normal force. Okay? Let's now go to part C. Student B is now climbing up the rope and has an acceleration of 0.25 meter per second squared with respect to the floor. What is the tension in the rope while student B is accelerating? So here is student B. We know their weight is still pulling them down, but now they have a greater tension force than their weight because their acceleration is upward at 0.25 meter per second squared. Newton's second law says that the net force acting on this student must be their mass times the acceleration that they have. This net force is found by doing the tension minus their weight. So the tension that we're looking for would be MBA plus MB times G, which means I can factor out the mass and add the acceleration to the acceleration of gravity. This is 60 kilograms times the 0.25 meter per second squared plus 9.8 meter per second squared. You work that out, 0.25 plus 9.8, that's sum times 60 with 2 sig figs. Well, it would be about 603 newtons. We didn't grade sig figs. 603 newtons. Now, part D, as student B is accelerating, is student A pulled up off the floor? Well, if I think about student A here, remember they have this tension, they have a normal force, and their weight acting on them. We now know this tension is 603 newtons. Their weight would be 70 kilograms times 9.8 meter per second squared. 70 times 9.8 is 686 newtons, which means that the normal force is not 0. So student A is not pulled up off the floor, right? Because there is a normal force. In order for them to be pulled up off the floor, the normal force would now be 0, and that's not happening here. Part E, with what minimum acceleration must student B climb the rope to lift student A up off the floor? So if student A is being lifted up off the floor, there is no normal force, which means that this tension must at least equal the weight of student A, which we now know is 686 newtons. So if I look at student B, where this tension is now 686 newtons, and their weight is pulling them down, and we found their weight, or could, 60 times 9.8, tells me that their weight is 588 newtons. So the net force that acts on student B would be the mass of student B times its acceleration. That net force is 686 newtons minus 588 newtons. This is 60 kilograms times their acceleration. So 686 minus 588 is 98 divided by 60, gives me an acceleration of roughly 1.6 meters per second squared. Okay? Let's now look at question 2. Here is this skier. We have a frictionless hill. There is a drag force. Let's draw all the forces acting on the skier. That is the incline. There is a normal force which acts perpendicular to the incline. The skier's weight is directed straight down, and then the drag force is directed parallel to their velocity. So that is the force F that they are referring to. Now, part B says find the terminal velocity. The terminal velocity means that the acceleration is 0, which means that that force F is going to have to balance the parallel component of the skier's weight. This would have to be B times VT. That is its magnitude. The negative on the velocity vector tells me it's opposite the velocity. That's all the negative is. It's not a magnitude. It's telling you a direction opposite the velocity. Their velocity is like that. So that's why the force is drawn anti-parallel to the velocity. The drag force here when they're balanced is BVT. This is mg sine of theta. So find VT. You had to use the variables in the question. So this M should be a capital M. So that VT would be mg sine of theta over B. And it's done. All right, let's look at question 3. Question 3 gives you all of these variables in the question. We have mu S1, mu K1, mu S2, mu K2. The masses are M1, M2, and capital M. And let's just go through it now. So part A, find the largest value of capital M for which the blocks remain at rest. This whole system is static, which means that masses 1 and 2 together are stuck together with a tension force pulling them this way, with a frictional force against the surface of this table, which is static. And we are told that with the table, the coefficient of friction between the table, static would be mu S2. So I'm going to say that's FFS2. We'd have their weight pulling down, which would be M1 plus M2 times G, and a normal force pushing up. The block of mass M would have its weight pulling it down, which would be capital MG, and that same tension force pulling it up. This tension and this tension are the same. This is not moving. So the tension is mg. So this is at rest, which means that the tension force is balancing the force of static friction with the table, mg. This is mu S2 times the Fn acting on that bottom block. What is that normal force on the bottom block? It's M1 plus M2, that quantity times G. The G is going to cancel, so that means M is mu S2, M1 plus M2, and that's my answer. Okay? Let's now go to part B. In part B, now suppose that mass M is large enough that the hanging block descends when the blocks are released, but blocks 1 and 2 are moving as a unit without slipping. Find the magnitude of their acceleration. So block 1 and 2, again, are stuck together, which means that their weight pulling them down is M1 plus M2G. The normal force acting up is the same. The tension would be pulling to the right. That force now of kinetic friction would be acting against the bottom surface, pulling them to the left. Again, with the tabletop, that's surface 2, right? If I look back here, the tabletop has the 2's, so I'm labeling that 2. If I look at mass M, I know its weight is now acting downward, and there is this tension acting up. I know that this is accelerating down, so this is accelerating to the right. I'm now going to write Newton's second law equations for each free body diagram. On this diagram, the net force that's acting would be M1 plus M2 times A, and that would be found by doing the tension minus the force of kinetic friction with the table. On this block, I would have that the net force is MA, and that would be mg minus the tension. The tensions are the same, so let me set my two tension equations equal to each other. It means this tension is M1 plus M2 times A. I'm going to add the force of kinetic friction, which would be mu K2 times the normal force, which is M1 plus M2 times G. And over here, This tension is mg minus ma. Let's set the two tensions equal to each other. I'm going to do that over here. So m1 plus m2 times A plus mu K2 times M1 plus M2 times G must equal capital MG minus capital MA. I want you to find A in terms of those variables. So I'm going to get all my A terms on the same side. And get all my other terms on the other side. So if I factor out the A, I'd have mg minus mu K2 times M1 plus M2 times G all over, factoring out the A, I'd have M1 plus M2 plus capital M, the mass of the system. And that is the answer to this question. Now, part C, suppose that mass M is large enough that as the hanging block descends, block 1 is slipping across block 2. Determine each of the following. So first I want to know the magnitude of the acceleration A1 on block 1. If I look, the rope is connected to mass 2, not to mass 1. So mass 2 would get pulled to the right, which means the kinetic friction force on mass 1 would be trying to pull that to the right as well. So here is little mass M1. There is a kinetic friction force pulling it to the right on the bottom surface. Its weight pulling it down is M1G, normal force acting up. That's it. There's no rope touching it. So the net force on this is M1A, which is equal to that kinetic friction force. So M1A is mu K1 times the normal force, Fn. What is the normal force acting on this block? It's M1G. Notice the M1 drops out. This is acceleration A1. So that is mu K1 times G. Now we're going to figure out what the acceleration of block 2 is. Here is block 2. That kinetic friction force on the bottom surface is trying to pull this forward, which means on the top surface, it's trying to pull it back. There is another kinetic friction force on the bottom surface, and then we have this tension force pulling it to the right. There is its weight pushing down, but so is block 1 above it. And then we have a normal force pushing up, and then mass M has its weight pulling it down, and that tension force pulling it up. This acceleration is A2. That is accelerating down, A2. All right, so let's write Newton's second law equations for each of these. The net force acting here, which is M2 times A2, would be the tension force minus the force of kinetic friction on the bottom surface minus the force of kinetic friction on the top surface. For this, the net force acting on this is MA2, and it would be found by doing mg minus the tension. What do I know about the tensions? They are the same. So that means this tension is mg minus ma2, and this tension is m2a2 plus ffk2 plus ffk1. Set the two tensions equal. mg minus ma2 is equal to m2a2 plus ffk2 plus ffk1. The left side stays the same. The right side, I have to replace these forces. This is mu K2 times the normal force on the bottom surface, which is M1 plus M2 times G. This is what we had here, mu K1 times M1G. So now I'm just going to solve this for A2. You do the algebra, pull it out. Factor out the A2. So this would be MA2 plus M2A2 on the right. Bring everything else to the left. Solve it for A2 and you get the idea, okay, on what you have to do. Please leave your test on the desk. I'll pick it up after you've left. Have a wonderful day. Textbook problems are due tomorrow.